Hi everyone. Today we're going to continue talking about scaling and the size of our universe and how we know. So for today, for this lecture, the outcomes are to define astronomy, understand why astronomy is studied, learn more about scientific notation, see it in use, learn about and be able to use the units of AU and light year, be able to convert to and from these measurements, and then to be able to discuss the steps in the scientific method and how scientific conclusions are made. So to start, we can think again about distance. So the astronomical units of distance, we say 1 astronomical unit, or 1 AU, is the average distance between the Earth and the Sun. So the distance between the Earth and the Sun is 1 AU. So we use that to compare. If something is 100 AU, that means it's 100 times the distance from the Earth to the Sun. 1 AU is about 92.8 million miles, or 150 about a million meters. So here is that number in scientific notation again. So 1 AU is a great way to think about larger distances, specifically in our solar system. So we can compare, say, the distance from the Sun to Neptune, compare that to the distance from the Sun to the Earth. Now, when we're talking about things even larger, when then even the amount of AUs would be quite large, we can switch to the unit of light year. So the light year is not a time, even though it does have the word year in it. It is another unit of distance, larger. It is the distance that light would travel in 1 year. So light travels at the speed of light, and in 1 year, that light would travel 1 light year. So it's equivalent to 6 trillion miles, or 9 quadrillion meters. So this is very, very, very large. So when we start talking about the whole universe, not just within our solar system, we will start using the unit light year. So again, light year is a distance. Even though it has the word year in it, it is not a unit of time. It is a unit of distance, about 6 trillion miles. So the speed of light that the light travels at is always... we use the letter C to denote the speed of light. And it's 3 times 10 to the 18 meters per second, or 186,000 miles per second. So here we have 1 AU shown here from the Earth to the Sun, that average distance from the Earth to the Sun. So as you'll learn as we go in this class, the distance from the Earth to the Sun changes just a bit throughout the year. So the average distance is that astronomical unit. If we zoom out in order to show the entire solar system in this figure, we would have to show about 107 AU, so about 100 times the distance here from the Earth to the Sun. So our whole solar system would take 107 AUs to show. So if we continue scaling outwards, here if we scale to where this box here covers 11,000 astronomical units, you'd see the Sun and the planets are there at that teeny tiny box, that teeny tiny square right there. You can't see the Sun versus the planets there. All you see is a little dot because we are so far zoomed out. If we zoom out even further, so about 1 million AU, which would be 17 light years, that means it would take, that's the distance that light would travel in 17 years. You'd start to see many stars around the Sun. If we zoom out even further to 1,700 light years, we lose the Sun completely in this picture of many other neighboring stars. If we zoom out to 170,000 light years, we'd start to see the Milky Way galaxy. So here is the Earth and the Sun, our solar system within our Milky Way galaxy. If we zoom out again by a factor 10. So now we're at 1.7 times 10 to the 7 light years. We lose the shape of the Milky Way galaxy. We just see it as a dot. If we zoom out even further, we would lose the Milky Way galaxy in the noise of the rest of the universe. So things get quite large when we're talking about our universe. And how did it all begin? So the universe began by what we call the Big Bang. So we know what happened during the Big Bang, but we don't know why it happened. So that is still a very active area of research within astronomy, is why did this happen? But essentially, in really short terms, the Big Bang started with all mass and all energy of the whole universe in one single point. And about 13.7 billion years ago, it exploded. And it's been expanding ever since then. So this unit here, GA, that means a billion years ago. If you were to see MA, it would be million years ago. So this is really common when we're talking about long time scales, is to see GA for billion years ago. So 13.7 billion years ago, we had the Big Bang, and we consider that to be the start of our universe, or the birth of our universe. So our galaxy within that universe is called the Milky Way galaxy. It is a spiral galaxy. It has this spiral shape. We will learn a lot about different types of galaxies later in the course. And here is our sun. You'll see it's labeled. This is where our solar system is located within our galaxy. So our galaxy has between 100 and 400 billion stars within it. So if you have ever traveled somewhere far away from light pollution, out in the desert maybe, up in the mountains where you're far away from bright cities, and you look up at night, you might be able to see an amazing sight such as this. So here you are actually seeing the Milky Way galaxy from Earth's viewpoint, is this very cloudy stripe across the sky. If you've never seen the sky look something like this, which I know at least in Orange County it is not quite possible to see very many stars, I highly suggest taking a road trip to get away from the lights and looking up at the night sky. So our solar system, we have the sun, and we have Mercury, Venus, Earth, this is us, Mars, Jupiter, Saturn, Uranus, and Neptune. These are the planets in our solar system. Please note that this figure is not to scale. Our solar system is made up of one sun, one star, 8 planets, many asteroids, most of them within the asteroid belt here between Mars and Jupiter, millions of comets, and over 60 moons between the 8 planets. All of the objects in our universe have very regular, smooth orbit. All of the objects in our solar system have a very regular, smooth orbit, and the orbits are determined by gravity, gravitational forces. So planets, the 8 planets, asteroids, and comets all revolve around the sun. Moons, however, orbit around their individual planets. So like our moon, it's not on this figure, but our moon orbits around Earth, but we on Earth orbit around the sun. So in our solar system, we have 2 types of planets, 4 and 4. So a planet is any spherical object that orbits a star that has cleared its neighborhood of objects. So that is the definition of a planet. It orbits a star, it is a sphere, or almost perfect sphere, and it has cleared its neighborhood of other objects, meaning that the gravitational force is so large that everything within its neighborhood or around that thing has eventually fallen towards that object. So the 2 types of planets we have are terrestrial and Jovian. So the terrestrial Earth-like planets are the first four. So Mercury, Venus, Earth, and Mars. They're very rocky, they're very small compared to others, and they're dense. The last four planets we call Jupiter-like or Jovian. They are large, they're very low density, and they're called gas giant planets. So that's Jupiter, Saturn, Uranus, and Neptune. So you'll see they're much larger than the first four planets. They're not as rocky, they're much less dense, they have a lot more gas than the terrestrial planets. So if you need help remembering the order of the planets, you can use this little cheat here. My very eager mother just served us noodles. So Mercury, M, Venus, V, Earth, E, Mars, M, and then Jupiter, Saturn, Uranus, Neptune. So that is a good way to try and remember the order of the planets. That is definitely something you're going to want to know early on in the class, is the order of the planets from the distance from the sun. So when I learned this cheat, it was actually my very eager mother just served us 9 pickles, because Pluto was a planet when I was originally taught, or was considered a planet when I was originally taught about our solar system. Upon further learning, Pluto is not a planet, so it does not fit the definition. So remember that a planet has to be spherical, it has to be orbiting a star, and it has to have cleared its neighborhood of other objects. So Pluto is not a planet because it does not fit that definition. It's part of the Kuiper belt, so it's actually in a belt of other objects that are very similar to it. So there's a couple of larger bodies out in the further distance of our solar system, so out past Neptune. Pluto is one of them. So Pluto happened to be the first one that was discovered. When it was discovered, we did not know about the other objects, so we thought that Pluto fit the definition. However, now that the other objects in the belt have been found, Pluto has been demoted, no longer considered a planet. So our Earth, we are the third rock from the sun. We are the third planet. We are a terrestrial planet. The nearest star is 4 light years away, besides our sun. And the Earth is about 4.5 billion years old. So I have a video that I want to show you that is a artist's rendition of the start of the universe. So it's a little bit of a long video. I'm going to skip through a little in the middle. But it's a time lapse of the universe. So it goes through the time lapse of the Big Bang and up until this point. There's a year bar along the bottom of the screen. So here we go. You'll notice down on the bottom it's going to have the label of time in million, billion years ago. So keep an eye out on that. I did not choose the music, let me just say, but please enjoy the incredibly dramatic music that they put to this very cool time lapse. So of course none of these are real images, it's all artist rendition and CGI. So here's that timeline.
From the primordial cloud of gas and cosmic dust, gravity forged the stars. Gravity connects star systems together in vast galaxies and steers them on their journey through unbounded space. relentless flow of time has driven the evolution of the universe and created extraordinary wonders. Some galaxies form so close together that they're locked in a gravitational embrace. What a magnificent sight it would be. As it evolves, the universe passes through distinct eras. Vast ages whose beginnings and endings are marked by unique milestones. The births and deaths of its wonders.
We are the product of a grand evolutionary sequence, cosmic evolution, about which we are only occasionally aware.
Gravity is the great creator, the constructor of worlds. The sun was formed. Clouds of hydrogen collapse further and further under the force of gravity, and the life cycle of a new star has begun. A star was born that would come to be known as the sun. Around it, a network of planets formed. Among them was the Earth. Debris left over from the formation of the solar system collides with the Earth. Earth began life as a molten hell.
The early continents were still forming. The land was dominated by volcanoes, hostile and lifeless. But deep in the oceans, life had begun.
So now we are at the point where, life has started. So that was a bit of a time lapse. Life has begun, and it's still many millions of years ago. So I have the link in the lecture slides if you want to continue watching that video or watch the middle part that I skipped out. But I hope that was a good rendition, a really nice dramatic rendition of how the universe was formed as in terms of what we know, as well as the amount of time that it took to get to where we are today. So how old are these different objects? We have the whole universe, 13.8 billion years old. So that is the age since the Big Bang. Our Milky Way galaxy started forming about 13.2 billion years ago. And then our solar system formed about 4.6 billion years old. We're almost halfway through the sun's life as a star. So we have about 6 billion years left before the sun dies. And our sun was formed when the solar system was formed, so 4.6 billion years ago. So these are very large numbers. It's very hard to conceptualize what is 4.6 billion years ago versus 13.2 billion years ago. So remember, the Big Bang was 13.8 billion years ago. The Earth is 4.5 billion years old. So the Earth is only 4.5 billion years old compared to the Big Bang happened 13.8 billion years ago. So I have one more shorter video today. Where is it? Here we go. That talks about how to understand the age of the Earth. So this isn't even going over the age of the universe, it's just the age of the Earth, that 4.5 billion years old.
How old is the Earth? Well, by counting the number of isotopes in a sample of rock that's undergone radioactive decay, geologists have estimated the Earth's birthday, when it first formed from a solar nebula, to be 4.6 billion years ago. But just how long is that, really? Here are some analogies that might help you understand. For example, let's imagine the entire history of Earth until the present day as a single calendar year. On January 1st, the Earth begins to form. By March 3rd, there's the first evidence of single-celled bacteria. Life remains amazingly unicellular until November 11th, when the first multicellular organisms, known as the Ediacaran fauna, come along. Shortly thereafter, on November 16th at 6:08 p.m., is the Cambrian explosion of life, a major milestone when all of the modern phyla started to appear. On December 10th at 1:26 p.m., the dinosaurs first evolve, but are wiped out by an asteroid just 2 weeks later. On December 31st, the mighty Roman Empire rises and falls in just under 4 seconds, and Columbus sets sail for what he thinks is India at 3 seconds to midnight. If you tried to write the history of the Earth using just 1 page per year, your book would be 145 miles thick, more than half the distance to the International Space Station. The story of the 3.2-million-year-old Australopithecine fossil known as Lucy would be found on the 144th mile, just over 500 feet from the end of the book. The United States of America's Declaration of Independence would be signed in the last half inch. Or if we compared geologic time to a woman stretching her arms to a span of 6 feet, the simple act of filing her nails would wipe away all of recorded human history. Finally, let's imagine the history of the Earth as your life from the moment you're born to your first day of high school. Your first word, first time sitting up, and first time walking would all take place while life on Earth was comprised of single-celled organisms. In fact, the first multicellular organism wouldn't evolve until you were 12 years old and starting 7th grade, right around the time your science teacher is telling the class how fossils are formed. The dinosaurs don't appear until 3 months into 8th grade, and are soon wiped out right around spring break. 3 days before 9th grade begins, when you realize summer is over and you need new school supplies, Lucy, the Australopithecine, is walking around Africa. As you finish breakfast and head outside to catch your bus 44 minutes before school, the Neanderthals are going extinct throughout Europe. The most recent glacial period ends as your bus drops you off 16 minutes before class. Columbus sets sail 50 seconds before class as you're still trying to find the right classroom. The Declaration of Independence is signed 28 seconds later as you look for an empty seat, and you are born 1.3 seconds before the bell rings. So you see, the Earth is extremely, unbelievably old compared to us humans, with the fossil record hiding incredible stories to tell us about the past, and possibly the future as well. But in the short time we've been here, we've learned so much, and will surely learn more over the next decades and centuries.
So that showed 4 really good ways to think about how old the Earth is, and you can then think about how old the universe is, because compared to human history, compared to our life, it makes up almost nothing compared to the history of Earth and the history of our universe. So we really have not been here all that long. So how do we know all of this? How do scientists study astronomy? How does science work? How do we know any of this to be true? How reliable are these conclusions? Are any sort of scientific conclusions? So scientists use what we call the scientific method. So this is the process where scientists form a hypothesis or multiple hypotheses, test them, gather evidence, gather more evidence, test again, do experiments, make observations, and determine if their hypothesis was true or not. It is the main system for learning, for establishing knowledge, for learning new things about anything. It's how scientists learn about Earth, about nature, about space, about astronomy, using this scientific method. So the scientific method is a little tricky. As a scientist, we don't use it step by step, in that we don't necessarily write out every single step, but this is the way that science is done and determined to be true. There's really precise terminology. Measurements have to be quantitative and very repeatable. So someone could come in and repeat your measurements, redo your observations and your experiments and get the same results. And your conclusions have to be supported by that evidence. So everything has to be provable, reproducible, and supported by evidence. That's how we know that something is true. So the first step is to identify the problem. So what problem are you working on? What question do you have? What are you trying to solve? And then you gather data. So gathering data could be a rock from the moon. It could be observing the position of a certain star night after night for a year. Gathering data that will help you understand the problem. Then you make a hypothesis. So you make a guess or a statement about what you think is true. So the really tricky thing about this is it has to be something that can be proved. So a hypothesis has to be yes or no. It has to be provable. So it has to be something that you can either say, yes, this is true, and here's why, here's my evidence, or no, this is not true, and here's why. Here's my evidence that proved I was wrong. So once you have your hypothesis, you then do your analysis and you test your hypothesis. So you do experiments using data. You gather more data. You do more analysis, do more experiments to try and determine if your hypothesis is true or false. Were you right or wrong? Either way, right or wrong, it's still science. So even if you learn, oh no, I was wrong, that is still a piece of science. You're still learning something new about this problem that you originally identified. So do your experiments agree with your hypothesis? It's either yes and awesome, you're right, your hypothesis is true. You might continue doing more experiments to have more and more evidence proving that you were right. Or no, it does not. So you go back to the drawing board and you make a new hypothesis based on these other findings. So the scientific method does not guarantee the truth, but it is as reliable as possible. So it's used to draw conclusions that are to the best of our current ability. So it's as reliable as possible at the time. So different hypotheses can be disproven in time. So this is generally due to increased evidence, updated technology, so new ways to gather evidence, data availability, so increased data, something like Pluto. So Pluto, being a planet, was disproven as we learned about the other objects in the belt with Pluto. So the more evidence that you have, the more reliable your conclusions are. So the stronger your evidence, the more reliable your conclusions, the more you can trust the conclusion of this method.